Mhm.
We're looking at one of the most fundamental and honestly one of the weirdest properties in physics, quantum spin.
It definitely challenges our everyday thinking.
Totally. So our mission here is to unpack all this material you sent, really try and get a grip on the nature of quantum spin itself, figure out how it connects quite directly, it seems, to frequency,
Right.
and untangle its relationship with the mass,
Hmm.
or maybe, the lack of a direct relationship.
Yeah, that's a key point in the sources.
By the end of this deep dive, hopefully you'll have some eye-opening insights all pulled straight from the material you provided. Let's jump in.
Okay, so quantum spin. The sources really emphasize right away that it's not what it sounds like.
Right, not a tiny spinning ball. The material is super clear on that.
No, it's an intrinsic property, something a particle just has, like charge, or like its rest mass. It's fundamental, and crucially, it's quantized.
Quantized. Okay, the sources stress this.
Yeah.
What does that actually mean for spin?
It just means it can only take on specific, discrete values. Think of it like having fixed settings, not a smooth dial.
Gotcha, like predetermined levels it can snap to.
Exactly. And these levels are defined by the spin quantum number, usually written as S, and the sources basically split all particles into two big families based on this number.
Right, integer spins versus half-integer spins.
Correct.
Okay, and that difference, the material suggests, is huge. It divides the world into fermions and bosons.
Precisely. Fermions are the ones with half-integer spin, so things like electrons, protons, neutrons, the stuff matter is made of, mostly.
Okay, electrons, protons, neutrons, half-integer spin.
And here's maybe the most critical consequence pulled straight from your sources. That half-integer spin for identical fermions, it directly leads to something called the Pauli Exclusion Principle.
Yes. The sources definitely highlight that one. Explain what that principle means again.
Well, it states that no two identical fermions, two electrons, say, can be in the exact same quantum state at the same time, in the same place.
And the sources really hammer home why that's so important, right? It seems like this abstract quantum rule, just based on spin, is basically responsible for chemistry, for the structure of atoms.
Absolutely. It's what forces electrons into different shells and orbitals around an atom. They can't all just pile into the lowest energy level.
So it creates structure, it makes atoms take up space, makes matter stable.
Yeah.
Otherwise, everything would just collapse.
Pretty much. Solid objects, complex molecules, they rely on this principle, which stems directly from fermion spin.
Wow. Okay. So what about the other family? The integer spin particles.
Those are the bosons. Think photons, particles of light, or the Higgs boson. They have spin 0, 1, 2, and so on, integer values.
And the big difference, according to the material.
They don't follow the Pauli exclusion principle. Bosons are perfectly happy to occupy the exact same quantum state. Ah, okay. And the sources connect this to things like lasers.
Exactly. In a laser beam, you have tons of photons all in the same state, which gives you that intense, coherent light. That wouldn't be possible if photons were fermions.
Or things like superconductivity, where particles condense into one state.
Right, that's another example where the bosonic nature is key. They can all pile up, unlike fermions.
Yeah. Okay. The sources also mention something else important about particles with spin, if they're charged.
Yes. A charged particle with spin automatically has what's called an intrinsic magnetic dipole moment.
Meaning it acts like a tiny magnet?
Essentially, yes. Yeah, like a tiny built-in bar magnet. And this is really important because it's the connection. It's how this abstract spin property actually becomes something we can, observe and measure.
Okay, so we have this intrinsic spin, it's quantized, it leads to huge consequences like Pauli exclusion, and if the particle's charged, it acts like a tiny magnet. How do we get from that to a measurable frequency? What do the sources say bridges that gap? The bridge is an external magnetic field.
Yeah.
When you put a charged particle with its magnetic moment into an external magnetic field, things happen.
Okay.
The sources explain that the particle's magnetic moment feels a torque from the field. The field tries to align the tiny magnet.
Like a compass needle trying to point north. Is it that simple?
Sort of, but there's a twist because of the spin. The spin gives it angular momentum. So instead of just snapping into alignment, the sources describe it precessing. It wobbles around the direction of the magnetic field lines.
It wobbles. Okay, I remember reading that. And this wobble isn't random, right? The material says it happens at a very specific frequency.
Exactly. A characteristic frequency called the Larmor frequency, usually written omega L.
Larmor frequency. And this is where the practical applications come in.
Absolutely. The sources stress that this Larmor frequency is the absolute foundation for technologies like nuclear magnetic resonance, NMR, and electron spin resonance, ESR.
And MRI scans in hospitals, that's related, right?
That is NMR, basically. MRI relies on detecting the Larmor frequency of typically hydrogen nuclei protons inside the water and fat molecules in your body when placed in a very strong magnetic field.
Wow. Okay, so the spin interacting with the field creates a wobble, and the frequency of that wobble is something we can measure and use.
Precisely. And the sources give the relationship. The Larmor frequency is directly proportional to two things: the strength of the external magnetic field, B.
Makes sense. Stronger magnet, faster wobble.
Generally, yes. And the other thing is the particle's gyromagnetic ratio, which is represented by the Greek letter gamma. So the formula is simply ALAB.
Okay, OL exists Gebi. What determines this gyromagnetic ratio A?
Well, the sources break it down. It depends on the particle's charge, Q, its mass, M, and another factor called the G factor, which is a sort of correction term relating the magnetic moment to the spin angular momentum. The formula looks like LAD times Q divided by 2 meter.
Ah, okay, wait, so mass is in there. Mass shows up in the gyromagnetic ratio.
It does. And that gyromagnetic ratio directly influences the Larmor frequency, OL.
So mass affects the frequency of the wobble when the spin interacts with a field.
Yeah.
But maybe not the fundamental spin numbers itself. Is that the distinction the sources are making?
That's exactly the distinction. Mass comes into the dynamics of spin in a field, but not the intrinsic definition of spins.
Interesting. Okay. And the sources also mention energy levels here in the magnetic field.
Right. The magnetic field doesn't just cause precession, it also splits the energy levels associated with spin.
Yeah.
For a simple spin 12 particle, like an electron or a proton.
Which have that half integer spin we talked about.
Exactly. Their spin can basically align either up or down relative to the magnetic field. And these two orientations correspond to two slightly different discrete energy states.
Two distinct energy levels created by the field interacting with the spin.
Yes. And the energy difference between these spin up and spin down states, let's call it dou, it is directly proportional to that Larmor frequency, OL. The relationship, based on Planck-Einstein principles, is EO, where I is the reduced Planck constant.
Okay, so the energy gap matches the wobble frequency.
Precisely. And that's the operational key the sources point to for NMR and ESR, because you have this specific energy gap, which corresponds to a specific frequency.
You can zap it.
Yeah.
With radio waves or microwaves.
Exactly. If you apply electromagnetic radiation at exactly the Larmor frequency, the particles can absorb that energy and flip their spin state transition from the lower energy state to the higher one.
And you detect that absorption.
You detect that absorption, or the energy released when they flip back down. That signal at that characteristic Larmor frequency tells you about the particles and their environment. That's how the abstract spin property gives you a concrete, measurable frequency signal.
That makes sense. It connects the quantum property to a measurable frequency through the magnetic field interaction and the resulting energy split.
Oh.
Okay. So spin is clearly linked to frequency in this observable way. Let's tackle the other big question from the sources. Spin and mass. Is a particle's fundamental spin number, SEPS, directly linked to its rest mass?
According to the material you provided, the answer seems to be a pretty definitive no.
No direct link.
There's no known universal formula that says, if a particle has spin X, its mass must be Y.
And the sources give some really strong evidence for this, don't they? They mention specific particles.
They do. The classic examples given are the electron, the muon, and the tau particle.
Okay, what about them?
They are all fundamental particles, leptons, actually. And critically, they all have the exact same spin quantum number. They are all spin 12 fermions.
All spin 12, okay.
But their masses are wildly different. The electron is the lightest, about 0.511 MeV0. The muon is much heavier, around 105.7 MeV0. And the tau is a real heavyweight, about 1776.8 MeV0.
Wow. Okay, so same fundamental spin, S12 for all three, but masses that are hugely different.
Exactly. That comparison, which is right there in the source material, is pretty compelling evidence against a direct, simple relationship between the intrinsic spin value and the rest mass.
Yeah, that seems hard to argue with.
It does, but remember where mass did show up.
In the gyromagnetic ratio, GU, the thing that affects the Larmor frequency.
Right. So mass plays an indirect role in spin phenomena, while the spin number doesn't determine the mass.
The mass does influence how the spin behaves dynamically in a magnetic field.
Precisely, because mass m is in the denominator of that formula, goop key to matter.
So if you have a heavier particle, assuming its charge and G factor are similar to a lighter one,
its gyromagnetic ratio, goop, will be smaller.
and since the Larmor frequency, GU equals goop times B,
A smaller GO means a lower Larmor frequency in the same magnetic field B.
So the heavier particles spin magnetic moment, wobble slower in the same field.
Exactly. So mass affects the frequency of interaction, the dynamics, but not the fundamental spin numbers itself. That's the key distinction the sources maintain.
Got it. And just to be thorough, the sources also briefly mention another frequency connection involving mass, something about de Broglie.
Ah, yes, the Broglie-Einstein relation. That relates a particle's total energy, E, which includes its rest mass energy, mc bar, to a frequency, f, associated with its wave-like nature. The relation is often written as F(a), where h is the Planck constant.
So that's a different kind of frequency, not the Larmor frequency.
Correct. The sources mention it likely to make sure we differentiate. The de Broglie frequency is about the wave nature of any particle with energy, while the Larmor frequency is specifically about the precession of spin's magnetic moment in an external magnetic field. Two distinct concepts, both linking energy or mass to frequency, but in different ways.
Okay, that clarifies things. So let's try and wrap this up. This has been a really fascinating deep dive into the material you shared. We've seen quantum spin isn't classical spinning at all. It's this fundamental intrinsic quantum number.
Quantized, taking only specific values.
Right, and that number determines if a particle is a fermion, half-integer spin, or a boson, integer spin.
Which leads directly to things like the Pauli Exclusion Principle for fermions, absolutely essential for matter as we know it.
And for bosons, it allows them to pile into the same state, explaining things like lasers. We also saw the very direct connection to frequency.
Through the Larmor precession, when a charged particle with spin is in a magnetic field, that frequency opal is the key to technologies like NMR and MRI.
And finally, we tackled the mass question. The sources strongly suggest no direct link between the fundamental spin numbers and a particle's rest mass, using that electron-muon tau example.
But mass does indirectly influence spin dynamics in a field, affecting that Larmor frequency through the gyromagnetic ratio.
Yeah. Hopefully this dive has given you listening a much clearer, maybe even a more surprising picture of spin, how this abstract quantum property connects everything from atomic structure to medical imaging.
It really bridges fundamental rules and practical technology.
So here's a final thought to leave you with, something to chew on from this exploration. Consider just how strange and powerful this is. A property like quantum spin, which isn't even spinning in any way we'd recognize,
Right, totally non-classical.
is somehow fundamentally tied to both the rules ensuring atoms don't collapse and the exact frequencies we use to see inside things. It makes you wonder, doesn't it? What other connections like that, linking seemingly unrelated phenomena, might still be hidden in the quantum world, waiting to be uncovered by the kind of research you shared with us?